Hello everyone, I'm Raza Kayani. Today's lesson I'm going to talk about mass, weight, and gravitational field strength. You are watching the revision series of high school physics. At the end of the video, I'm going to explain and solve some interesting exam questions related to mass and weight. By the end of this lesson, you should be able to show the understanding the idea of the mass of a body. You will be able to describe what is meant by the weight of an object. You should be able to state weight is a gravitational force. You will be able to differentiate between mass and weight. And at the end, we are going to recall the use of equation mg to calculate weight. The amount of matter contained in an object is called mass. The symbol of the mass is m. It is the amount of stuff in an object in any form. It could be gas, liquid, solid. Mass is measured in kilogram. So as I said, the symbol is used m for the mass. That's the quantity. We have another symbol m for meter, that's the unit. So you have to make a difference between the quantity and the unit. 1m is for mass as a quantity, and m for meter is a unit of the length. Now we can talk about weight. The force exerted on an object by gravity is called weight. It is denoted by W. Weight is a measure of gravitational pull on an object by Earth due to gravity. It is measured in newtons. So that pull could be a Earth, Mars, Jupiter, Moon, or any star. So in this table, we are going to make a difference between mass and weight. Mass is a scalar quantity and has no direction, whereas weight is a vector quantity and is always directed towards the center of the Earth. Mass of a body is always constant everywhere in the universe. Weight of the body varies from place to place. Mass of a moving body is given by m equals F over A or m equals W divided by G. Weight of a body is given by W equals to mg. Mass can be determined by a normal balance in grams or kilograms. Weight of a body is measured by spring balance in newtons. SI unit of the mass is kilogram, but the SI unit of the weight is newtons. Now we can practice some questions. What are the correct units for mass and for weight? So we are going to see here the options. In option A, it's kilogram and kilogram. Both are the same one, so both cannot be same. So in B, mass is in kilogram and weight is in newtons. That's the correct one. Next question. What is the meaning of the weight of an object? A, the density of the material from which it is made. That's not possible because weight has nothing to do with the density. The force exerted on it by the gravity. That's correct, okay, because the weight is nothing, is the only force exerted by the gravity. So the answer is B. We can look option C and D in this case. The mass of the matter it contains. No, weight is not the mass. The pressure it exerts on the floor, weight has nothing to do with the pressure in this case. We can try another question. A child sits on a rubber ball and bounces up and down on the ground. What stays the same when the ball hits the ground? So we are going to see the quantity that stays the same when the ball hits the ground. So the first is A, the acceleration of the ball. No, the ball is moving in different directions, so acceleration cannot be the same. The mass of the ball, yes, mass stays same everywhere, so that can stay the same. The shape of the ball, that's not possible, even the shape is changing, deforming. And the velocity of the ball, as direction is changing, so velocity is also changing, so the correct answer is only B. After making a difference between mass and weight, we can talk about gravity. A natural force that pulls all objects towards the center of the earth is called gravity. Gravity has a stronger force on the thing with greater mass. So that means gravity is directly proportional to the mass. More the mass, more the gravity. Gravity is a force of attraction that exists between any two objects. It's any two objects. They could be small, they could be big, so the gravity exists between both. If we have an object over here, and one object here to the left, one object to the right, and one object at the bottom, so what will happen to that object when we throw in different position? So they will be acting toward the center, so they will fall here toward the earth. So the gravity is always acting toward the center of the earth. Wherever we drop an object, that's going to fall toward the center. So the gravity is acting toward the center. If you see this astronaut and the earth, so it's being attracted towards the earth, toward the center of the earth over here. So the gravity is applying force always towards the center. So the gravity is acting towards the center and pulls every object towards itself. As we mentioned earlier, the gravity is acting downward always toward the center. So whenever we want to do work against gravity, we have to apply the force. If you want to jump, we need a lot of force. Similarly, if you want to carry the weight against the force of gravity, to lift the weight, we need a lot of force and practice to work against gravity. There is a force of gravity between the sun and the earth, between the earth and us, and even between two protons. The satellites, planets, galaxies, and clusters of galaxies are all intact by the gravity. Sun's gravitational force makes the earth move in an orbit around the sun. So all galaxies, they are attracting each other. As the solar system, they have a force of attraction. Similarly, galaxies, they have a force of attraction and keeping the shape of the universe uniform. If we look at the diagram, the Earth is orbiting around the moon, and that has its own orbit, and the moon is going to move around the Earth. There's a force of attraction between sun and earth, and there's a force of attraction between earth and moon. The tides are being produced due to force of attraction between water and moon. So wherever moon goes close to the surface of the water, the tides are produced. So we can see it every day, the tides being produced by the attraction of the moon. Acceleration due to gravity. The acceleration produced in a freely falling body due to the attraction of the earth is called acceleration due to gravity. It is denoted by g. So what can we say that here in this case? The weight is directly proportional to the gravity. More the mass, more the weight. Double the mass, the weight is going to be double. If you have a triple mass, then weight of the object is going to be 3 times. So whenever we change the proportionality into equality, we are going to complete the formula by that way, W equals to mg. So the unit of the W weight is newtons, and the value of the mass is kilogram, and the value of the g is meters per second squared. The acceleration due to gravity is independent of the mass of the object. So acceleration doesn't depend upon the mass. We are going to see a few examples here. If I have a bag of sugar, if the mass of the sugar is 1 kilogram and the weight of the sugar is 10 newtons, and if the weight of that person is 90 kilogram and weight of the person is 900 newtons, if the mass of this car is 1,200 kilogram and the weight of the car is 12 1000 newtons, then we can calculate the value of the G to see that is the value of the G independent or dependent upon the mass. Now we can calculate the value of the G to see that is the gravity is independent of the mass or it depends upon the mass. So the formula for the value of the G is always W weight over mass. So I can use the same formula over here. So weight of the sugar is 10 newtons, and I'm going to divide by 1 kilogram, and I'm going to get the value 10 newtons per kilogram in this case. Now I can try here for the person. So weight of the person is 900 newtons, and 900 newtons divided by 90, and I'm going to get again 10 newtons per kilogram. In case of the car, the weight of the car is 1200 newtons divided by 1200, and I'm going to get again here 10 newtons per kilogram. So these all objects, they have a different masses, but the value of the G is same. So that proves that the value of the gravity is independent of the mass. Whatever the mass of the object, the value of the G remains the same. The Earth is pulling every object with the same rate, that is 10 newtons per kilogram, or we say it 9.8 newtons per kilogram. Now we can practice one more question over here. Before solving this question, I'm going to write the data given in the question. To calculate the weight, we have a formula W equals to mg. So in case of Earth, I'm going to put the value for the G for the Earth here. So the mass remains constant, that is 50 kilogram, and the value of the G is 10 newtons per kilogram. So kilogram can be cancelled by kilogram. So the weight is going to be 500 newtons. So the weight is going to be 500 newtons. Now I can try another weight for the distant planet. That again, the formula is mg, and I'm going to substitute the value in. So the mass of the planet is same, that is 50 kilogram, and the value of the G for planet is 4 newtons per kilogram. Again, kilogram can be cancelled by the kilogram, and I'm going to get here 200 newtons. So now I'm going to see the option, which one is the correct answer. So 5 and 12.5 is not possible. That value is also very low for B, that's not also possible. And C, 500 kilogram and 200 kilogram, but I have got unit newtons over here, so that is also impossible. So the correct answer is D, where we have a 500 newtons and 200 newtons. Now we can talk about Earth's gravitational field strength. The gravitational field strength at the surface of the Earth produces force of approximately 10 newtons on every object of mass 1 kilogram. Gravitational field strength is the weight acting on per unit mass of an object. Mathematically, G equals W over M. We can say that weight per unit mass is the value of the G. So where G is the acceleration due to gravity, that is 10 newtons per kilogram on Earth. The Earth's gravitational field pulls everything towards its center. So the value of the G for other planet is different. So this value is only for Earth. The value of gravitational field strength is different on different planets because it depends on the mass of the planet. As Jupiter is the most massive planet in our solar system, so the value of the G of the Jupiter is about 25 newtons per kilogram. If the gravity of the planet is stronger, the object feels heavier. If the gravity is low, the object feels lighter in weight. If we see in this case, the mass is only 56 kilogram. On the moon, the value of the G is only 1.6 newtons per kilogram. So by multiplying 56 by 1.6, we are going to get approximately 90 newtons. On Earth, the value of the G is 10 newtons per kilogram. So by multiplying 10 with 56, we are going to get 560 newtons weight on Earth. When the gravity changes, weight of the falling object also changes. The gravity changes due to mass of the planet. More the mass of the planet, object or star, more the gravity. So in this case, we can see for same mass, the different weight on different planets. Look at the Mercury, the weight. And now see the difference on Venus. And see the difference on the moon. And now the weight on the Mars. Similarly, we can see on Jupiter and on other planets. If we note that the weight changes from place to place, but the mass remains same. We are going to consolidate the same idea to see the different weight on different planet by calculation. If we have an object of mass of only 70 kilogram, and by using the same formula, if we are going to multiply 70 by 3.7, we are going to get 266 newtons weight on Mercury. Similarly, for 70 kilogram, if we are going to multiply with 8.8, that's the value of the G on Venus, and we are going to get this much newtons here, 616 newtons. On Moon, the value of the G is less, so the weight on the Moon is going to be 112 newtons in this case. And on Earth, the value of the G is 9.8 or 10 approximately, so we are going to get 686 newtons weight on Earth for a mass of 70 kilogram. Similarly, on Mars, we are going to get 266 newtons, and on Jupiter, we are going to get 1,750 newtons weight of the mass of 70 kilogram, because the value of the gravity on the Jupiter is highest in the whole solar system. You can stop the video for some time and try to solve the question by yourself. On a newly discovered planet, an object of mass 8 kilogram has a weight of 64 newtons. The gravitational field strength on the planet is, we are going to calculate the value of the G on that planet. We know the formula of the weight in this case, W equals to mg, but we are going to get the value of gravitational field strength, that is G, W over m. So in that case, the weight is 64 newtons, and the mass of the object is 8 kilogram. So in that case, the value of the G is going to be 8 newtons per kilogram, and the option is going to be A in this case. All these options are not correct. Now we are going to practice another question. A piece of steel is taken from the Earth to the Moon for an experiment. The gravitational field strength on the Moon is smaller than on Earth. Which statement about the piece of the steel is correct? A, it has less mass on the Moon than on Earth. That's not possible. Mass remains the same. It has more mass on the Moon than on Earth. The mass remains same again. C, it weighs less on Moon than on Earth. Yes, the value of the G is less on Moon as compared to Earth. So that is the answer of the question that we have. Now we are going to practice another question. The table shows the weight in newtons of a 4 kilogram mass on each of 4 planets. So in the table, we have 4 planets over here: Earth, Jupiter, Mercury, and Venus. Here is the value of the weight given for the 4 planets. the diagram shows a force meter being used. That's the force meter being used. On which planet is the force meter being used? So we are going to choose from here A, B, C, on which planet the force meter is being used. So here we can do the calculation first. So first of all, what we are going to do, the formula to calculate the value of the G equals W over M. So we are going to use the same formula because that is the weight given in newtons. So weight given in newtons divided by mass, according to the formula, that is 10 kilogram. So we can find the value of the G in the table. So that's going to be 100 divided by 10, that's going to be 10 newtons per kilogram. So now similarly, we are going to calculate the G for the weight of 250 newtons. 250 divided by the mass remain the same, that is 10. So I'm going to get 25 newtons per kilogram in this case. So the value of the G for Mercury, 40 divided by 10, that's going to be 4 newtons per kilogram. And in case of Venus, the value of the G, 90 divided by 10, that's equal to 9 newtons per kilogram. Now, I'm going to see for this planet. So I'm going to use the same formula here for planet. So we know the formula that we have used for G, that is G equals W over M. Now I'm going to see the value of the force, 18 newtons, and the weight is 2 kilogram. And my answer of the G over here is 9 newtons per kilogram. So 9 newtons per kilogram is for Venus. So I'm going to choose the answer D in this case. Practice 2 more questions by calculation, not by multiple choice. So here, a rocket built on the space station has a mass of 750 kilogram. Calculate the weight of the rocket on the Earth. So the formula for the weight is W equals to mg. So we are going to see the mass. Mass is 750 multiplied by 10. It is on Earth. So we can find the weight 7. So we can multiply mass with the value of G to calculate the weight. 750 multiplied by 10. That is 7,500 newtons is the weight of the rocket on the Earth. Now we are going to practice another question. A space probe has a weight of 147,000 newtons on Earth. Calculate the weight of the probe on Mars. So here, the weight is given on Earth, and they want us to calculate the weight on Mars. First of all, I have to calculate the mass of the object. So the formula to calculate the mass is M equals W divided by G. So the weight is 147,000 newtons divided by 10. So the mass is going to be 14,700 kilogram. That's the mass of the probe. Now we are going to use the formula of weight, W equals to mg, to calculate the weight of the probe on the Mars. So the mass is 14,700 multiplied by value of G on Mars. We take 3.7 or 4 approximately, so we can multiply by 4 to get the weight in newtons. Now, finally, we can talk about gravitational field. The space or region around the Earth within which it exerts a force of attraction on other planets, on other bodies, on other stars is called the gravitational field. Sun's gravitational force attracts all the planets to move in an orbit around the sun. Earth's gravitational force pulls every single object towards the center of the Earth. Finally, we are going to see the relationship for the acceleration due to gravity with and without air resistance. If you look to this diagram on the left, so the both balls, they fall at the same time. In the second diagram, an object and an elephant, they are also falling with same acceleration. But to the diagram on the right, there's an air resistance acting on the ground. That's the reason the hammer, it reaches earlier as compared to the feather. So that experiment was done on the moon, and when astronauts, they dropped hammer and feather at the same time, they reach at the same time to the surface of the moon. That proved that there is no air resistance acting at the surface of the moon. Now we are going to practice another question. A brass ball and a feather are released at the same time. On Earth, the ball reaches the ground first. On the moon, they reach the ground at the same time. What is the explanation for this? So we are going to see the option. Now we are going to see the first option. Both weigh the same on the moon. That's not correct. Mass is directly proportional to the weight. More the mass, more the weight. So both, they have a different masses. So we cannot say both weigh the same on the moon. Both weigh less on the moon. Again, that's against the relationship of mass directly proportional to the weight. There is a greater air resistance on the moon. No, there is no air resistance on the moon. So the last option, there is no air resistance on the moon. That's why they fall at the same time on the moon, but they don't fall at the same time on the Earth. Those students, they want to practice more question. I have collected a range of past paper questions from 2002 till 2019 from different variants being examined by the University of Cambridge worldwide. The answers to these questions are available on the website. So I have the question from paper 4 and from paper 6. Thank you for watching. Subscribe to the channel to receive the next lesson.